So with that, I'd like to introduce our next speaker. This presentation is for the paper that received the Meta Sozen Award for Excellence in Structural Research. And Meta Sozen was my advisor as a graduate student, so it's very meaningful to me as well. Couldn't ask for a more fantastic mentor. The paper is Strength Reduction Factors for ACI 318 Strut and Tie Method for Deep Beams. This will be presented by our author, Victor Aguilar Vidal.
Okay, good morning everybody. Thank you for being here, and thank you to ACI for awarding the Sozen Award to our paper. This paper, I wrote it during my time at Auburn with the help and guidance from Dr. Barnes and Dr. Novak. And it's titled Strength Reduction Factors for ACI, Strut and Tie Method for Deep Beams. Since this is a short presentation, it has only 3 sections: an introduction where I'll touch base on what I mean by reliability, a little introduction to the strut and tie methods and the provisions in the code. I'll show you the basis of our reliability analysis, and then our conclusions that are essentially the recommendation for strength reduction factors when designing using this method. And if somebody's curious, that's, front page of the paper if you want to look it up. So let's start by addressing the question of how do we deal with risk in structural analysis. And the answer for that is in this figure here, which is essentially understanding and accepting the resistance of the member in blue, and the load effect on that member in red are not deterministic values. Okay? They are not unique values, they carry uncertainty. And therefore, if I do the difference between R and Q, I get, namely, the safety margin, that green line there. And eventually, I could run into the possibility that R, the resistance, is less than the load effect, giving me, that shaded area that we call probability of failure, which is always there. The trick is to limit it to a small value that we feel comfortable with. How do we do that in the practical designs? Well, by using our design equations, where we need to make sure that our reduced resistance is greater than the factor load. Those factor loads are based on the uncertainty of the load components. The resistance factors, phi, also called strength reduction factors, are based on the uncertainty in the resistance. And this is really important because we're going to come back to this concept later. And the idea is that the combination of these factors in our design equation will give us a certain predefined probability of failure, a target probability of failure. But since we don't like that sentence in particular, we rather talk about reliability index. So the target reliability index is essentially the acceptable minimum safety margin that we're going to use for our design. And we express that in terms of reliability index, and we put the beta sub t, okay, target beta. In previous calibrations, the value 3.5 has been extensively used for the calibration of girders and beams, and in the strength limit states. Here we have a little corresponding probabilities of failure just for references. But what is important is that if we want to or we should select target values to reduce the probability of failure, like larger target values to reduce the probability of failures of less desirable failure modes. So if for flexure we are accepting a 3.5, ideally for shear, that is, a less ductile failure mode, less desirable, we should go a little higher. Ideally, 4 has been recommended in other researchers. So that is regarding the reliability part. Now, about strut and tie. In this method, the complex stress field of a given concrete structure is represented by a truss, by an equivalent truss. And we like trusses because they are easy to solve. The issue usually is how to define the truss. But the elements in compression in this truss are called struts. The elements in tension are called ties, solid lines in these pictures, and the intersections are called nodes. This method has been proven very useful to design complex structures, D regions, like the ones in these pictures. Regarding the provisions in the code, for each one of the components, for the struts, nodes, and ties, we have to apply this design equation, and each of them has a phi factor, which in our code is, all of them are the same, 0.75. I learned strut and tie during my internship designing bridges years ago, and I knew that the phi factors were different. So why and ACI are all the same? And then I learned reliability from Professor Novak, and I learned that the phi factor should be related to the uncertainty in the resistance. So why are all the same? If when we look at how we calculate, how we compute the strength of the strut and nodes, we realize that they are mainly depending on F prime C. And for the ties, they're mainly depending on Fy. And if we look into the test data, the uncertainty on F prime C is about a 15%, but for Fy is just 3%, so 5 times less. So why are all the phis the same? And that is what motivated this research, where we investigate the strut and tie provisions regarding the reliability and also the likelihood of observing a ductile failure. I'll talk more about that when we start digging into the results. We also determined the current safety margin that was not done up to date before for individual components and for the whole member that we use a deep beam as an example. Then we selected an appropriate target based on current designs and suggest phi factors accordingly. So this is a deep beam, a very standard. On the top is a deep beam. In the bottom we have the strut and tie model. This is a statically determined model. Simple truss. It's a series system, meaning that if one of the elements fails, the whole system will fail. And since this is an approximation to what will happen in reality, and we don't know exactly where the ties are, we don't know exactly where the struts are, we play a little bit with the geometry to come with this conservative estimation that the component forces could vary around 20% from what is predicted in the model. Luckily, Professor Park and Kushma gathered a rather large database in the past where they compare the experimental strength of deep beams compared with the prediction from strut and ties models. And in this plot we have that ratio, tested strength divided by predicted strength as a function of F prime C. And we started to see some relation here. So if we plot the same information using box plots, in these box plots the lower lane is the minimum, the top is the maximum, the blue box includes 50% of the information, and the red lines is the mode. And based on this, as many other researchers have also noticed, the conservatism of these predictions is not uniform across compressive strength. So we decided that for normal strength, concrete will use one model, and for high strength concrete will use a different model to take this into consideration. This table summarizes all the probabilistic models that we use for our reliability analysis. All of them are expressed in terms of two parameters, bias factor and coefficient of variation, that are essentially mean and standard deviation in a normalized way. Essentially, everything was consistent with previous calibration of ACI, except for the analysis uncertainty that was derived specifically for this model in this paper, based on the consideration that I showed you just a few slides ago. So different models for normal and high strength concrete, and also a consideration that the forces that we predict with the strut and tie might not be exactly what will develop in reality. So with all the pieces together, now we're able to compute reliability of individual components. On the left side, we have the reliability on the y-axis as a function of the load ratio, dead load as a function of total load. And we see that for struts and nodes, those reliabilities are between 3 and 3.5, but for ties on your right, the reliabilities are beyond 4.5, which means that the struts and nodes are more likely to fail than ties. So in a system, if it fails, it more likely will start by crashing the struts, splitting the concrete, than yielding the ties. That is what we want. To address the probability of failure or the reliability of the whole system, we use this inequation that is related to how correlated the members are. So assuming that the struts and nodes are fully correlated because they are made of the same concrete, and assuming that all the ties are also correlated because they more likely will come from same mill for at least one single element, and that there is no correlation between the concrete components and the ties, we can approximate the reliabilities of the system. This table summarizes results for normal strength concrete. For each component, strut, node, and tie, we have the phi factors. Okay, we have different sets of phi factors that were tested here. The first one in bold is current practice in ACI 318. Beta sub I is reliability of each individual component. Beta sub system is the system reliability index. And the column that says P RT less than RSNC is essentially the probability that the failure will start by yielding the tie. So let's call it the likelihood of observing a ductile failure mode. So current practice give us a system reliability of 4, which is actually great. Since this method has not been calibrated based on reliability before, it was surprising that it actually went to 4. That's great. The issue is that more likely than not, the failure mode will not be ductile. So for the 100 millions of simulations that are run, I couldn't observe one single case where the failure was ductile. If we modify the phi factors to 0.65 and 0.9, the reliability increases slightly, and also the likelihood of ductile failure mode will also increase slightly. For high strength concrete, the system reliability is just 3.2 in current practice, and the probability of failure mode that is ductile is also fairly slow, just 0.3%. And with the modification that we want to propose, the reliability again goes up a little bit, but the likelihood of a ductile failure mode increases dramatically. So current practice essentially gives us a reliability index 3. We tend to summarize or approximate these numbers to 3, 3.5, 4. So it's essentially 3, which is less of the threshold that has been used in the previous calibration. So it's lower safety, if you want to call it like that. And with the modified phi factors that we're proposing, we almost reach the 3.5 that is the target that was used for flexural limit state in the past. So it's not still the ideal case, but it's better than what we have today. And with that, the conclusions from these studies are that the current resistance factors in the strut and tie method in ACI 318 promotes the likelihood of a non-ductile failure mode relative to a ductile failure mode, and therefore we believe that the phi factors in this method require some attention. The level of conservatism of the strength predictions with ACI 318 strut and tie method varies with concrete compressive strength, and this is an observation from many researchers, and which results in inconsistencies in the reliability of these designs. We found out that for normal concrete strength, the reliability is about 4, which is great, but for high strength concrete, the reliability is lower than one would expect of applying the code. Therefore, our suggestion is that we should use 0.65 for strut and nodes and 0.9 for ties, which slightly will increase the system reliability across all ranges of concrete strength, and will also increase the relative probability or likelihood of observing adactyl failure mode. And with that, I'd like to say thank you again for this wonderful award. We're really happy and proud. And also thank you for being here. So.